Hello! Today we're going to talk about exponential rules and rational numbers. But first, there's a warm-up. Pause the video here and see if you can solve these problems. Okay, so we want to see if each relation is a function. So we know each relation is a function if each input has exactly one output. Meaning we can't have an input go to two different things. If we look at this first one, we have inputs of 2, 4, 5, and -3. This one gets the old green check because yes, it is a function. No x value repeats, meaning no x goes to two y's. If we look at the second one, however, b up at the top, we realize that -2 goes both to 7 and -2 goes to 6. That makes this just a relation. The reason it's a relation is because we have -2 going to 7 and 6, and we don't know which one. For C, we can look at this and do the vertical line test. We see that no matter what, this will work, and there is no vertical line where it'll hit two values on the graph. Okay, so before we move on to exponential rules, I want you guys to try this problem out. Pause the video here and see if you can write the function rule with it. All right, so a lot of you probably wrote C equals 50m plus 100. And that's okay, but I want to show you a different way that we could write this. And it's C of m equals 50m plus 100. The reason that this is important is because we want to know that the cost of this function is with regards to how many months we do. So now when it wants us to find out what, let's say, what does it say? 6 months, this would be C of 6. Meaning the cost at 6 months would be 50 times 6 plus 100, and that ends up being $400. For 8 months, it's C of 8 equals 50 times 8 plus 100. And I know a lot of you might be looking at this and saying, Mr. Erb, I just knew to multiply 8 by 50. Why do I need to worry about this notation? Well, we're going to see this notation in a couple different ways, and especially going into Math 1, we want to feel comfortable with function notation, right? This C of something else, this f of x, you're going to see that a lot. So here are three different functions. All three of these things are functions, right? We have a linear, we have something, this is called a quadratic. It's okay if you don't know the name of quadratic, but we're going to find f of or g of or h of that value. So notice how this one's f of, and so we would use f for this one. For this one it's g, so we're going to use that function. I'll use some yellow here. This one is h, so I'll use that value. So try to calculate, pause the video here and try to calculate those values. For the first one, I got 3 times 4 plus 7, which is equal to 19. So f of 4 is equal to 19. For g of 6, I plug it in, and I have a negative, and then 6 squared plus 7. So I'm not squaring the negative, I'm just squaring the 6, and this would give me negative 36 plus 7. So negative 36 plus 7 is equal to negative 29. And then for the final one, I have to plug that value in twice. So here it'll be negative 2 squared, and then 3 times negative 2, and then plus 1. So the quantity negative 2 squared means we're applying that square both to the 2 and the negative. So I get out a positive 4 because the quantity negative 2 times negative 2 will give us 4. And then 3 times negative 2 is a negative 6, and then finally a plus 1. And so we add those all up. Our final answer is negative 1. So let's talk exponent rules. These are three great rules, well, two great rules for us to have written down in our notes. If I have two quantities multiplied together and they have like bases, we're able to add up the exponents. If we have two like bases and we're dividing, we can subtract the exponents. An easy way to think about this is, let's say we were to have 2 squared times 2 to the 4th. A lot of us may know 2 squared is 4, and 2 to the 4th as 16. This is really 4 times 16. If we multiply that out, we get 64. If we want to rewrite 64 as powers of 2, we'd actually get that it's 2 to the 6. It wouldn't be 2 to the 8, right? Which, if that would happen if you were to try to multiply the exponents, we're actually adding these exponents up to end up with 6. The same thing could happen if we were to think about, let's say 10 to the 6 divided by 10, or let's do 10 cubed, right? We wouldn't say, oh, well, that's just going to end up being, 10 squared. 6 divided by 3 is 2. We'd end up getting 10 cubed because we're going to subtract. We subtract and we would get 6 minus 3, which is 10 cubed. If you want to think about how you've simplified tens before, right, you would say, oh, I'm going to write it all the way out. I'm going to expand it, and then I'll just simplify out the zeros, right? We're essentially dividing by 10 every time we simplify this out, and we're left with 10 cubed. So I want us to try to multiply these out. I'm going to walk you through one, and then I want you to do the rest. Okay, so I'm going to walk you through one, and then I want you pausing. In this first one, I have to make sure I distribute x to everything inside. So 3x times x means I add up the exponents. So that's 3x squared. And then x times 2 gives me a plus 2x. Now I'm going to distribute out this whole negative 1/4, and I get minus 1/4 x. And then minus 5 makes this a plus 5/4. My final step is to combine all the stuff on the inside. And so I'm not allowed to simplify the x squared with the x because they are different powers, right? The base of x may be the same, but they have different exponents. And like terms have the same base, and same exponent. So the only two terms in this one I can simplify down would be the 2x and the negative 1/4 x. This one would keep the 3x squared in front, and we always want to keep highest powers out to the front and then kind of lower it down. So we want descending order, right? We're going to start at the greatest and go down to the least. So we have 3x squared, and then minus, let's see, 2 minus 1/4 would be 1 3/4. And if we want to convert that to an improper fraction, that would make it, what, 7/4? So minus 7/4 x, and then finally plus 5/4. So notice how I only have one x squared, one x, and one constant, right? We only have one of those terms. Here's one, there's the other, and there's the third. So we don't have those repeating. And then lastly, we see the exponents going in descending order. We start at x squared, then we work our way to x to the first, and then finally we finish with no exponent. All right. Let me actually pause the video here and try this second one out. I have full confidence in you guys. In worst case, you can come back after you're done and go from there. So pause the video and try the second and third one out if you're feeling adventurous. So for the second one, what I'm going to do is distribute out this 2. So I get 2x squared. Distribute out the 2 to the negative 6 gives me a negative 12. And the 5x times 4 gives me a plus 20x. And then the 5x times negative x gives me a negative 5x squared. So our next step is to simplify and combine like terms. So the only thing I can combine are these x squares. So 2x squared minus 5x squared would be negative 3x squared. So I get negative 3x squared. Next comes the x, so just plus 20x. And then finally the constant, the minus 12. All right, next one, final one. We distribute out this 8. So we get 8x squared. Distribute out the 8, we get 24. The plus 7x is kind of just hanging out by itself. We leave that alone. Next, the negative 4x times 2x becomes a negative 8x squared. And the negative 4x times the negative 6 becomes a positive 24x. If that was confusing how I was doing all those, try to just rewatch the video and see if slowing it down or rewatching it again will help you out. Now I can combine my x squares. So 8x squared minus x squared, well, that would be 0x squared. But we're not going to write 0x squared. We're just going to write no x squares down. Then 7x and 24x can simplify to get 31x. And then finally a plus 24. All right. So let's work our way down. We're doing the power rules, but I also want to introduce the zero power rule. So when we're working this through, I want you to think about what's happening. What are we doing with each number? So if I get 2 to the fourth, 2 to the fourth is 16. Let's use a brighter color. 2 to the fourth is 16. 2 cubed is 8. So my power went down by 1, which meant that I was dividing by that base, right? Essentially 2 to the fourth, or 2 to the third, is equal to 2 to the fourth divided by 2 to the first. So we're just simplifying down each time. So this 2 squared would be 4. Again, we're dividing by 2. 2 to the first would be 2. And so that means 2 to the 0 has to be 1. This also tells us that 2 to the negative first would be 1/2, because we're dividing 1 by a half. And then next, 2 to the negative second would be 1/4. Let's try that out with the second one. So this would be 4 zeros. Switch to blue. This would be 3 zeros, 2 zeros, 1 0, no 0. And a lot of you might want to be like, oh, let's put the decimal point, right? But we know that that's also equal to 1/10. And then the next thing we can do is say, now it's 0.01, which is 1/100. So let's kind of come up with a rule here. First of all, we have two things. Zero power rule, right? If I have a to the 0, where a is a number other than 0, we can't have a be 0. A to the 0 is equal to 1, right? Assuming this is in parentheses, a to the 0 is equal to 1. It doesn't necessarily have to be in parentheses, but that's important if we were to have like a negative out front and doing anything like that. The next thing we want to know is that if we have a negative exponent. So let's say we had a to the negative x. This is the same as 1/a to the x. The reason we're able to do this is because I know that if I were to take a to the x and I wanted a positive exponent, I'd have to multiply by a to the x over a to the x. Now, this is a to the negative x over 1. So what ends up happening is this is a to the negative x plus x over a to the x. Well, a to the negative x plus x is a to the 0. And we just said a to the 0 is 1. So it's 1/a to the x. And there you go. All right, let's look at one of these simplified down. So what we can do here is we can combine these out, right? And we can say, 4 to the negative 10th times 4 to the 5th would be 4 to the negative 5th. Because remember, it'd look just like this. 4 to the negative 10th plus 5, and that would give me 4 to the negative 5th. We're going to keep that 4 to the 7th in the denominator. We don't need to deal with it yet. But what this tells us we can do is we can now divide again. Dividing means we're going to subtract our exponents. So this is 4 to the negative 5 minus 7. So division means subtraction of exponents. This would be 4 to the negative 12th. You could write it as 4 to the negative 12th, or a lot of times we'll write it as 1/4 to the 12th. Both of these would be acceptable answers, and they're equivalent. All right, why don't you guys try these three out? What I would suggest you doing, if you're still a little lost, have me watch me explain the next one, and then you try out the other two. Okay, but pause the video now if you want to try them out. Otherwise, be ready. I'm going to keep moving on. So here we realize that this is 8 to the 5th times 8 to the negative 2nd, or to the negative 7th. That'll give us 8 to the negative 2nd, because 8 to the 5 plus a negative 7 is 8 to the negative 2. That denominator still stays the same as a to the, or 8 to the 12th. And so we can simplify this down by subtracting the exponents. Division means subtraction. So we get a to the negative 14th. We could also rewrite this as 1 over 8 to the 14th. And there you go. All right, next one. I'm gonna do a cross. If I do not have an exponent there, that's the exact same thing as having an exponent to the first. So 10 to the 4th times 10 to the 1st will be 10 to the 5th. And we're dividing by 10 to the 6th. So division means subtraction of exponents. And this gives me 10 to the negative 1st, which is the same thing as 1 over 10th. For the last one, we'll do over here. Now, we notice in this case, we have stuff in the numerator and denominator. So let's see what that'll look like. So we'll get 7 to the 10th in the numerator, and then 7 to the 8th in the denominator. And that's just me adding up the exponents. Now when I simplify, I'd get 7 to the 10 minus 8, because division means subtraction of exponents. We get 7 squared. And that's where we'd stop it, right? We could also write this as 49 if we want, but either one of those would be okay. We would not write 1 over 7 to the negative 2nd. That is not something we'd want to write. So we'd probably leave it as this. All right, I want you to try these out with, well, actually, let's try these out together. We're going to combine bases and their exponents. So x to the 4th times x squared is x to the 6th. Y to the 5th and y to the negative 11th would be y to the 16th. For the bottom, 4 times 7 would be 28. X squared times x cubed would be x to the 5th. And then y to the negative 2nd times y to the 5th would be y to the 3rd. And that's where we leave it. Okay, why don't you try this one out? Oh, sorry, we don't have any practice. All right, what is a rational number, you may be asking? And I would probably ask you during a math club. A rational number is a number that can be written as a division of integers. Now remember, an integer is a positive or negative number. So essentially any number that can be written as a over b, where a and b are integers. An irrational number can't. That's pretty much what it is. An irrational number is not a rational number. So not a rational number. An irrational number pretty much just means essentially no ratio. No ratio. So let's talk about some examples of these. For a rational number, we can have mixed numbers. Mixed numbers are okay. Improper fractions are okay. Oh, sorry. Proper fractions are okay. Improper fractions okay. Slap a negative on it, it's fine. Negative 4.6 would be okay. So rational numbers also include terminating or repeating or repeating decimals. If you have a terminating or a repeating decimal, yes, it is rational. If not, it's irrational. So let's go over some examples. 8.2, is this rational or irrational? It's rational, right? We can write that as a fraction. In fact, we could write it as 82 over 10 and then simplify that down to 41 over 5 if we wanted to. So this is good. What about 4.1234 dot 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 dot? Is that rational or irrational? That's going to be an example of irrational. We don't have a fraction that we can represent that, and we don't know what's happening after the dot dot dot. What about 2.121212 dot dot dot? That's going to be a rational number. Notice how this 1, 2 repeats. So we can write this as 2.12 repeating. If you want to go into how you can actually convert that into a fraction, we could talk about that, but this would essentially be 12 over 99, which simplifies down to 4 over 33. What about, let's get crazy. What about the square root of 7? Yikes. The square root of 7 cannot be simplified down and therefore is an irrational number. Let's compare that to the square root of, like, let's say 100. 100 we can actually take the square root of and get 10. That one's okay. But let's say we had the square root of, I don't know, 300. Well, 300 we can't take because it simplifies down to 10 square roots of 3. And so, in fact, 10 square roots of 3 or 300, that's going to be an irrational number. All right, so let's talk about some examples. You try. I want you to determine if these are rational or irrational numbers. Go for it. So this first one is irrational. Pi is irrational. It never ends. We can't write it as a fraction of integers. The second one, 2/3, well, that's already in a fraction, so that's rational. For this, 1.2222222, that's good. That's 1.2 repeating. We could write that as 1 2/9, and therefore that's rational. Notice the fact that it's repeating. That's the big thing. Which brings us to number 4. This is also rational because we have the 31 repeating. This would be 4 and 31 over 30, or 31 over 99. This fifth one, this is also rational. It's my best attempt at trying to write a mixed number, but it's still okay. Here, this is also irrational. 40 over 19 is already as a fraction, so we're good to go. Square root of 5. Square root of 5 is irrational. We can't simplify it down. Square root of 36, however, is 6, and 6 is a rational number. Then lastly, square root of 200. The best we can do is 10 square roots of 2, but regardless, we still have the square root of 2. So this is an irrational number. All right, guys, well, that's all I have. I'm sorry for the longer video, but it's got a lot of good stuff in here. I would make sure to take notes, make sure you were doing the handout. And again, any questions you have, let me know. I would be more than happy to help you out. So have a good one and hope to hear from you soon.